Okay, so hopping right into 8.4. Today we're solving log and exponential equations. So, and you, I mean, honestly, you kind of already know how to do this. We've already scratched the surface of this quite a bit in our graphing and our evaluating units. So just as a reminder though, if the variable, what you're solving for, is in a log or is in an exponent, basically if it's locked in the log or in the exponent, and it is very much locked, like you cannot mess with it when it's in there. You cannot do math with it. You can't divide log off of the argument. They're one and the same. Okay, so it's locked. The way we solve that is by one of two methods. Either we use the one-to-one property, which is, well, we used it yesterday and the day before, where we got to cross out the bases. You know, we get to, if the bases were the same, we got to cross them out. We can use that property if we can get the bases to be the same. And that property works for logs too. If each side of the equation is a single log with the same base, then we just get to cross out the logs. Okay, so that one-to-one property works for exponents and logs, same base. So either that is our strategy, or our plan B, our backup, is to convert it into the other form, to rewrite the equation into the other form. Okay, and just as a reminder, log bases and arguments are restricted to only positive values. Only positives allowed in the log. So if x was in a log at one point in time, then you need to check your answer to make sure that wouldn't give you a negative in the log, that x value wouldn't violate the rules of logs. Okay? So here we go. Number one, I just need you to make a series of observations when you see these equations. The first observation I need you to see is that x is trapped. It is in an exponent. And you don't have a way of getting that out. You might be like, well, couldn't we divide the 9 away? No, because it's not 9 times 2x, is it? So dividing away is what we use to take multipliers off of something. But it's not. 9 is not a multiplier. It's the base of an exponent. So that's not the same. Our strategy is either get them to be the same base, or if we can't do that, convert. So can we get 9 and 27 to be the same base? Yes, they're part of a power family. What power family? 3. Okay, so 9 is 3 to what power? Squared. Yeah, 9 is 3 squared. So I just changed 9 to 3 squared. That's still a 9. Do we all agree that's still a 9? I haven't changed the value. I just changed the form. It's 3 squared. And it's still being raised to the power of 2x. And then 27, I'm going to change that to 3 cubed. And so that's a 27. And it's still being raised to the power of x minus 1. What do I do with exponents when I raise a power to a power? I multiply them. So this really is 3 to the 4x. And then 3 to the, here's how we multiply those exponents. 3 times x minus 1. It's this whole exponent times this whole exponent. So it has to distribute into it. The 3 has to distribute into the x minus 1 because they're multiplying. Okay. So now we get to cross out the bases. I'm not dividing by 3. That's not what's happening. I'm ignoring the 3. I'm disregarding it. So 4x equals, and I'll go ahead and distribute the 3 also. 3x minus 3. Subtract 3x from both sides. X equals negative 3. Okay? Easy peasy. All right, if you're good with that, why don't you try number 2? And then if you feel good about it, show off to your neighbor. And check your answer up here. A couple of first steps there for you. If you're stumped, a couple of first steps for that number 2. Both base of 3. Okay, that's what I got. Negative 6. Anybody else get that?
Me too.
Wonderful. Wonderful. All right, number 3. Yeah, it sure is nice to be him, isn't it? Okay. Number 3. First observation, x is trapped. So that sparks a question. Can I get the same base? No. 9 and 35 are not in the same power family. They never will be. Not with whole number exponents, at least. So we're going to have to convert this. So we're going to follow our loop. What form of equation is it presently in? Exponential. Yeah, it's in an exponential form right now. So when I convert it, please, for the love of math, don't convert it into another exponent. We convert to a log. So from an exponent, we go to a log. Or if we were in log and we needed to convert, we would go to an exponent. Don't try to convert back into the same language. So we have log base 9 of 35 equals x. Now this is your exact form. The instructions, if you saw them, they asked for both an exact form, or what we call calculator ready form, or also an approximate form to 3 decimal places. So this is your exact form. There's no rounding here. This is the exact value. To go into the calculator, to put it in the calculator, you need to go to the math screen, the math menu. So grab a calculator. If you don't have one, grab one of mine or one of yours. Grab one that can do logs. Okay, so there are 2 ways to type this in your calculator that I want to cover. The first way is by using the log base. Most of you in your calculators have this feature. It's in the math menu, so you go to math. It's the button right underneath alpha. And then the 11th option in that screen is log base. So you have to scroll down to log base. And then that allows you to type in your own base. You can just type in log base 9 of 35. Make sure you always close the parentheses on your argument in a calculator. So log is going to naturally supply an opening parenthesis for the argument. Close it, especially if you're doing any math with that log. Okay, so I get an approximate answer of 1.618. Okay, 3 decimal places, thousandth place. But the other way I want you to know about is called our change of base formula. And this was quite an important feature when logs were done by hand, or when the first calculators came out that could do logs. So log base 9 of 35, for the longest time, we would take that and we would change it into a different form that went like this: common log of 35 divided by common log of 9. Okay. And this is also an exact form of our answer. And you can check it in your calculator. The common log button is right next to 7. Common log of 35, close those parentheses, divided by common log of 9. And it still makes our exact decimal form, okay? It's just, it's a different way of evaluating that log. So, one, if you're ever having to use a calculator that can't do log base, this is your alternative. 2, you still need to know it. Like if you're taking the SAT, there are log questions on the ACT. There are log questions on the ACT, and they could very well ask you something like this, not in the form of, I can just use a calculator. You know those question writers. They can write a question however they want to force you to solve it however they want you to solve it, okay? So just know that this is out there, change of base formula. All right. All right, hey, if you're feeling pretty good about that one, why don't you try number 4, 5, and 6. We're going to roll through these. Okay, you just try these and check your answers up here as you finish them up. I'll put my answers up as well. So you're on number 4 here. Remember, I want the calculator ready, or exact form, and also an approximate decimal, Okay, there's number 4. As you finish up, check number 4, and if you're good on number 4, move on to number 5. Number 5. Okay, number 5, initial observation. X is trapped, so I either can get the same base or I can convert. Am I ever going to get the same base with a 7 and 15? No, we're going to have to convert, okay? Remember, for the love of all things math, convert to the other form. This is an exponential form. Convert to a log. So log base 7 of 15 equals 9x, and then divide by 9. What gets divided by 9? The log, the 7, the 15, what? Everything. The whole thing. Can I divide those pieces up and do them by 9? No. No, I cannot divide those by 9. The 7 and the 15 are sewn into the log. They are inseparable. Okay, you can do no math with those separate from the whole thing. So when we divide by 9, the entire thing is dividing by 9. So x equals log base 7 of 15 divided by 9. That is your exact form. And then your approximate form log base 7 of 15, close those parentheses if you need to, divided by 9 is 0.155. Okay. Let's do a quick review of rounding, because it's come to my attention that not everybody learned, not everybody was taught how to round properly. We'll just put it like that. So here's a number here, like 3.43749, something like that. And I said round to 3 decimal places. So some of you have been taught that, oh, okay, I need to round to this place right here. That's a 4, but wait. The 9 next to the 4 bumps it up to a 5, which then gets to bump the 7 up to an 8. And some of you have been thinking that that's how rounding works, that it has like this cascading effect from the left, like dominoes. Every big number on the left ever gets to bump the next one up. No. If you're rounding to 3 decimal places, you look at that 3rd decimal place and you only look at the number next to it. You don't look any further. It doesn't matter what's on the other side. Okay? So that doesn't round up. It's just 3.437. The 4 doesn't get any help from the 9. Okay? Otherwise, people would go around and tell me 3.49 rounds up to 4.
Wow.
No.
Yeah.
No, it doesn't. It doesn't round. Nobody would be like, it's about 4. What? No, it's not. It's closer to 3. Okay? So, just a little bit of rounding for you, rounding review there. All right, number 6. Number 6. First observation, X is trapped. I'm either going to get the same base or I'm going to convert. Am I going to get the same base with E? Probably not. No. So, I'm going to have to get the exponent alone. What's the exponent? What exactly is the exponent? What part? E to the negative 0.3x. That's the exponent. Everything else is not the exponent and needs to be gotten out of the way. So we'll move the 7 first, add 7 to the other side. 4e to the negative 0.3x equals 20. And then we will divide by 4. That's the first crucial error some people make. Divide that 4 away. It is not part of the exponent. E to the negative 0.3x equals 5. Now we can convert. So we're following our loop. Next crucial mistake. Here it is. You ready? Here's what people write. They're so silly. I bet you know it. I bet you know what it's going to be.
It's going to go right to exponent.
They write that.
Wow. Uh-oh.
Oh my gosh. And I get it, because E is so foreign, it doesn't really look like a number, and so we're not thinking of it as exponential because it's associated with log, and so we're like, it's a log, I'm going to exponential. No. You're going from exponential into a log, so you have to write the log. E has its own log called ln. And yeah, E is part of it. It's the hidden base of ln, natural log. Also, by the way, that's not in. A few of you are writing in. It's L for log. Okay? So ln, natural log of 5 equals negative 0.3x. And then divide by negative 0.3. So x equals natural log of 5 over negative 0.3. There's your exact form. The natural log button is next to 4. Natural log of 5 divided by negative 0.3. So negative 5.365. Okay, is that what you guys got?
Yes.
Perfect. All right, so moving on to solving log equations. Log equations have the same 2 strategies. I need you to make the observation. X is trapped. It's trapped in a log on number 7. Second observation. Can I get the same base, or do I already have it? Yeah, I still have the same base. Log base 4 equals log base 4. Okay, so if I have the same base, I can disregard the base. I'm not dividing log away. Okay? So I'm not breaking my rule about things are locked when they're in the log. I'm disregarding them. It's the one-to-one property. If everything else in the equation is identical, the two missing pieces must also be identical. They must be equivalent. So 2x plus 8 equals 6x minus 12. And I'm solving from there. I get that as an answer. And you had better check that. Because remember, when x is in a log, it has to be a number that would follow the rules of the log. What is the rule of the log? Positive arguments only. X's can be negative. The log just can't be left with a negative. Okay, so plug in your x value and see if it would be left with a negative. Log 2 times 5 is 10 plus 8. That turns into log 18. That's fine. It's positive. I don't even care that it's 18. I just care that it's positive. And then 6 times 5 is 30 minus 12 is log 18. Cool. Don't care that it's 18. Care that it's positive. It's positive, so I get to keep my answer. If it was log of a negative, I would cross it out and write no solution. If it fails even one log, it fails the whole problem. Okay? All right, try number 8. Try number 8 on your own. All right, there's number 8. X equals 3, yeah, sure, but when you plug it in, it leaves you with log of negative 1, which is not allowed. You cannot have a log of a negative. So look up here. You really can't tell by what x is whether it's going to work out or not. X can be positive or negative. Okay? A positive x isn't a guarantee that it works. We just saw it fail. And a negative x value isn't a guarantee that it fails. It could work out. You just have to plug it in and see for yourself. Okay? All right, let's keep going. Why don't you try number 9? What's the first observation? X is locked. So I can either eliminate bases by having the same base on both sides. Is that going to happen here? No, I don't have a log base 7. There's not another log base 7. Now, there are ways to bring a log into an equation. And if you want to know about that, you can ask me after the lesson if you want. Okay. But for us, there's no other log in there, so I'm going to have to convert this to get x out. Isolate the log. What's the log? The log, the base, and the argument. Isolate that part, and then convert. As you finish up, check your answer there as you finish up. If you're good, move on to the next one. Okay. So we have to isolate the natural log here, because we're never going to get this side to be natural log in our class. And so we get natural log of negative x equals 4.5. Remember, natural log has a base of e, so when we convert, that's going to be the base of our exponential expression. E to the 4.5 equals negative x. Please do not do 2.7 in your calculator. That's not going to get you the right answer, and you're going to be counted wrong if you do that. Let's see what it becomes if you use 2.7. Negative 2.7 to the power of 4.5. It's 3 off. You'd get 87.3. That is not the same, and that will be wrong. Okay? There's no reason why you can't be using e. We're not in 7th grade. We don't use 3.14 for pi anymore. We use pi. And we don't use 2.7 unless we don't have a calculator and we're graphing it. Okay? We have a calculator, use the full decimal. All right? Okay. Number 11. Why don't you try number 11 on your own? Check it up here when you're done. Quick correction there. 0.017, rounding correctly there. Okay. Number 11. There's number 11. So on number 11, we had to convert it right away. Okay? And then we knew right away this was going to be a factoring problem. You know, you have x squared and you have x. Those are never going to come together. So you're going to have to solve by factoring. Remember, when you're solving by factoring, you're totally allowed to divide a number out of both sides. You just can't divide out the variable that you're solving for. So you can't divide both sides by x, but you can divide both sides by 3, no problem. Make the factoring easier on yourself, and then don't forget to set the factors equal to 0. Because these x values were in a log, we need to check them to make sure they work. Make sure that they give us positive arguments for that log. Okay, so they're good. They both work out pretty cool. All right, there's one question I want us to do that's not here. Here it is. So we just call it 12b or 11b. 11. It's not really connected to 11b, so it's weird to call 11b, but it doesn't matter. Here we go. The question is 2 times 4 to the x equals 16 to the 3x minus 1. So write that down, and let's think about how we would solve this. Can I do 2 times 4?
No.
No. 4 is locked, just like x, okay? Because it's got an exponent, right?
Get everything done.
So you think about our strategies. What's observation number 1? X is trapped. It's in an exponent. So your 2 questions are, could I get everything into the same base?
Yes.
Yes, pursue that if it's possible. So 2 times 4 is 2 squared, still being raised to an x, equals 16 is 2 to what? The 4th. Still being raised to the 3x minus 1. And we're raising a power to a power, so let's go ahead and address that. 2 times 2 to the 2x equals 2 to the, I'll distribute the 4. 12x minus 4. Cool. Now everything is the same base. Can I cross out the bases? No. Why not? They're all the same base.
No, they don't have all of an exponent.
Hey, look, it's not 1 to 1 if it's not 1 to 1. This is not one exponent over here. There's 2 different bases here. I mean, they're the same base, but there's 2 terms. It's got to be 1 exponent equal to 1 exponent, 1 to 1. Okay, so how can we bring these together to make them 1? They both have the same base. What is the exponent rule? When you're multiplying 2 terms that have the same base, what do the exponents do? They add, right? And you're like, what? What do you mean? Yeah, x squared times x to the 3rd, that's x to the 5th. We add the exponents when the bases are the same and we're multiplying. So that's what we're doing here. This becomes 2 to the 2x plus 1 equals 2 to the 12x minus 4. Okay, and now we can cross out the bases. Now it is truly 1 to 1. And we can solve for x from here. Okay. Number 12. The amount radium in grams. A couple of typos in here. I'll fix them as we go. The amount radium in grams of radium present out of an initial amount, not dose, amount. Right. Out of an initial amount, which is R sub O, after T years can be modeled by the equation here. So this is our equation. A final amount of radium, that's R, is equal to an initial amount, R sub 0, times e to the power of this exponent that has time in years right there, okay? So that's our equation. They're asking how many years will it take for 100 grams of radium to decay to 15 grams, okay? So first of all, they're asking how many years. They're asking me to solve for a time. So my answer is going to be T equals. I'm solving for time. How many years? That's a time question. Will it take for 100 grams to become, right, to decay into 15 grams? So what is your final amount here? 15, not 100. We're decaying. It's losing mass. So this is our final amount. And the 100 is where it started. That's our initial amount, R sub O. So we're just plugging their numbers in and solving for what they asked us to solve for. So when we plug things in, here's what we get. 15 equals 100 times e to the power of negative 0.00043 t, solve for t. And we follow our sequence of thoughts. What's the first observation? T is trapped. Will we ever be able to get same bases? Not with e. So we need to isolate the exponential expression, then convert. Is 100 part of the exponent? No. It's a multiplier in front of the exponent. Divide it off. Watch out for e. Make sure you're actually doing a conversion into the other form. For some reason, e just trips people up. They think they've converted when they haven't. Why don't you see if you can finish this one on your own? All right, there's your final answer. Is that what you guys got?
Yeah.
Okay. Okay. Hey, that's it for our notes. So now you know how to solve log and exponential equations.